All right, so we're going to do a quick review of a concept you discovered or discussed in geometry, but it's a good idea to refresh your minds before we move on to the next concept in trigonometry. And it comes from, if I were to give you an angle labeled A and a side length B, and then if I were to identify for you that side length A equals N, say, form a triangle. You might say, well, no problem. There it is. This is angle B. Done. Easy peasy lemon squeezy. Problem is, that may not be true. You can't just assume there's a triangle. And if there is a triangle, you can't assume it lives here. So let's look at some special cases to evaluate. Let me do a little bit more labeling just so it's easier to work with. So if I have a side length C, a side length A, angle C, and I'm going to keep this in my hypothetical brown because I'm not really sure where B is yet. So let's look at the possible outcomes or the possible cases. Suppose the length of A is less than B, but it's not long enough to actually intercept with the line AB at some point. So A is less than B and A is less than the actual height of the triangle, H. Well, in that case, what you get is just an arm or a leg that just swings freely in space and never actually is able to form a triangle. The next case is that A is less than B and A is exactly the same height or the same length as H, in which case you would get a right triangle. Now, the other case, the third case, you're looking at A is less than B, so you wouldn't have an isosceles triangle, which is a possibility, but A is less than B, and A is greater than H. If A is greater than H, then the case that you've drawn could be correct, right? You could have an angle B here, that's your case 1B, or it could swing all the way around and actually intersect the line AB here, which would give you the case 2. In either case, notice you're dealing with an oblique or obtuse angle. In the first case, the oblique or obtuse angle would be at C, and in the second case, it would be at B2. So before you can solve a triangle using any method, you would have to be assured that you're even dealing with a triangle. And if you are dealing with a triangle, which case are you dealing with? So in quick recap, if A is less than B and less than the height of the triangle, you have no solution or no triangle. If A is less than B and exactly equal to the height of the triangle, you have 1, and it's a right triangle, excuse me. And finally, if A is less than B and A is greater than the height of the triangle, it's less than B, so you have a triangle, but it's greater than the height, you have 2 triangles or 2 solutions. Let's do an example. You're given the information A equals 15, B equals 12, and angle A is 94 degrees. So we're dealing at this point with an obtuse or oblique angle. So we know we are going to have to look at the ambiguous case. So a 94 degrees, slightly larger than 90 or than a right angle, A. And so A is 15, side length A is 15. Side length B, I'm going to label this one B, but side length B is 12. So that makes this angle B and this angle C. So we know we're dealing with an obtuse triangle, so we have to evaluate whether it's an ambiguous case. But we're lucky in this case because our obtuse angle happens to be the angle that we have identified already. So we're looking at this case here, this pink case, where we know that C in this case is the obtuse angle, so we know that there's exactly one solution because it has to be just the B1. So we can just continue on from here solving for our side lengths. I'm not going to solve for the values because that's our next lesson. This lesson is just about identifying and evaluating the ambiguous triangle. So let's look at another example. In this case, we're given A equals 9, B equals 11, and A is 61. So if I sketch this one out, it's almost immediately obvious that the only angle I know is not the oblique angle. It's an acute angle, which means I'm going to have to do more evaluation to determine what kind of triangle I'm dealing with. So I know that B is 11, which if I were to label this side B and this side C, then what I have is some case where this equals 9. Since 9 is less than 11, I'm confident that this is not my triangle, but I'm not really confident where my triangle actually is. So I'm going to evaluate for the ambiguous case. A is less than B, because 9 is less than 11. So now I just need to know, is A less than H, in which case I have no triangle? Is A equal to H, in which case I have one triangle, a right triangle? Or is A greater than H? And the only way to do that is to determine what H must be. So this would be H. And unfortunately, H is automatically a right triangle because that's the one I'm looking for. And unfortunately, I don't have enough information to really find that using the Pythagorean theorem, but luckily I have some trig. So I know that the sine of 61 degrees is equal to the opposite, H, over the hypotenuse, 11. So H is equal to 11 times the sine of 61. Let's pull up the calculator. The sine of 61 times 11, 9.62, let's go 1, 9.621. So I see that side A is less than H, and so there is definitely no solution or no triangle. And of course, if I had returned a value or received a value for the length of H as less than, so say it were 8, so say H equaled 8, then 9 would be longer than 8, so I would have two possible cases, and I'd have to find them both.